Okay, so this video is on calculus, and before we start, I should mention calculus, algebra, a lot of these subjects really deserve their own series if you want to go in depth and understand a lot of the ins and outs. The point of this series is for people who've already taken these courses and they just kind of want a little bit of a refresher. So a little refresher on vector algebra, a little refresher on some algebra, a little refresher on some calculus. Maybe it's been a few semesters. It's not meant to necessarily be a replacement if you've never taken the course. You can still watch this video and it'll help, but that might be its own series if that's something people want to watch. So let's start with this. X as a function of time is equal to x naught plus v naught t plus 1/2 a t squared, where these guys are all constants and t is the only variable, which is what's implied with this. But okay, so we have this, and if you've taken physics before, you'll see this is an equation of motion. It's a kinematic equation of motion, actually. And if not, then that's okay. But the first thing we want to do is we want to find the derivative of x with respect to time. That's the first thing. So the way we do that, d by dt of x naught plus v naught t plus 1/2 at squared. And an important property of derivatives is that they're linear. And one of the properties of linearity is that this derivative, you can almost think of it as being able to distribute over addition and subtraction. So this simplifies to just d by dt of x naught plus d by dt v naught t plus d by dt 1/2 at squared. And just for the sake of demonstrating another property of linearity, you can factor constants out. So we mentioned v naught is a constant, 1/2 a, those are constants. I'm going to pull those outside of our argument. The x naught, you could do it, but it's not going to simplify the problem at all because of what the derivative of a constant is. And really, even with these problems, it doesn't necessarily make it easier to solve. But I do want to just show that property because I feel it's an important property that will make your life a lot easier if you have to do calculus. So first off, the derivative of a constant is 0. If you ever forget that, just think of what a derivative means. If we have a function, a constant function, let's just say this is, y equals 4. Think of what the derivative means geometrically. It's from a geometry point of view, it's the slope. It's the slope of a line. Particularly, the derivative is a slope of a tangent line of some function. So at that point, what is the rate of change? Well, for a constant function like y equals 4, that never changes. There's no change, there's no slope. So that's why it's 0, if you ever forget. The slope of t, that's kind of like asking what the slope of y equals x is. It's just 1. So this ends up just being 1 times v naught, so that's just v naught. Plus, and in case you forgot the power rule, if you have a x to the n is f of x, then f prime of x, this is Newton's notation, this is Lambda's notation, this is with this little guy up here, that's Newton's notation. The way we do this is you bring your exponent down and you subtract 1. So that's your power rule, generally speaking. So if we do that over here, what's the exponent? It's 2. 2 times 1/2, that just drops. And 2 minus 1 is just 1. So it's just a times t. And this is the derivative of x with respect to time. The next question, using the same function, is what's the second derivative of x with respect to time? And this is Lambnitz notation of writing that. And all you do is you just take another derivative. So I went kind of slow the first round. Let's go a little quicker here. The derivative of v naught, right? That'll be just 0, and then this goes away. So this, we're left with just a. The t just turns to a 1. Cool. So we found our second derivative. And if you're not sure how we did that, like I said, I can make a series on calculus. This was my other one. I can make a series on calculus, but you can also just rework it really slowly how we did before. I also want us to interpret a little bit of what this means, the second derivative. Or kind of thinking with the second derivative what this means. So what happens if a is less than 0? Well, there's two ways you can think about this. One, you could just go back to the function here and see this is a parabola, right? It's a quadratic. And when a is positive, right, we just have our traditional quadratic. When a is negative, it's reflected down like that. But another way of thinking of that is with concavity. And that's basically how the graph bends. Now, when x is less than 0, you have concave down, sad face. When x is greater than 0, concave up, happy face. And the way we can also interpret this is the concavity can help us determine if we have, a max or min. So if we have x is less than 0, we could have a maximum. Over here, we could have a minimum. So that's kind of one of the interpretations we can have from the second derivative. It tells you the bend of the graph is kind of the important part, and that can help give information on if it's a max or min. Okay, let's try taking a more complicated derivative. Let's say we wanted the derivative with respect to time of a cosine of omega t plus phi. So the d by dt is telling us, this is like a command, it's like an operation. It's telling you to take the derivative. And we'll also make a note that the a, the omega, and the phi are constants. Well, the a, using linearity, that could just be factored out. That's probably the first thing I would do. Okay. Now, this requires us to know a little bit of the derivative of our trig functions and the chain rule. So let's see. The way we do this is the derivative of cosine. If you don't remember the chain rule, I'll do that over here. The chain rule slowly is f prime of g of x times g prime of x. I'm going to go a little quicker and just do this. The derivative of cosine is negative sine. We keep this inside part, and then we multiply by the derivative of the inside, which looks like it's just omega, right? This gives us omega, and that's 0. So just cleaning it up a little bit, that's negative a omega sine omega t plus phi. And that is your derivative. So like I said, if you guys aren't comfortable with the chain rule or your trig derivatives, maybe a series on calculus would be a little better, which I could do. But I'm assuming you've taken calculus, you know the chain rule, and you're just looking for math that'll make your life a little easier in physics. Okay, let's look at the next one. f of x is x over cosine of x. And we want to know the second or the first derivative. Well, first off, I'm going to rewrite this using one of our properties with our trig functions, and that's the reciprocal. So you have your cosine of x, your sine of x, your tangent of x. The reciprocal, the way I like to remember it, these are your reciprocals. I'll tell you how I remember it in a second. The cos go with the non-cos. So cosine goes with the non-cosecant. Sine goes with the cosecant. Tangent goes with the cotangent, which that one's pretty easy. So this is the same thing as x times secant of x. You could have solved this just using the quotient rule, but I did want to show that property with our trig functions because sometimes it's helpful when you're working through an equation to algebraically manipulate it a little bit. And now we can actually use our other rule, which is the product rule. So that's f prime g plus f g prime. And we'll let f be x, and we'll let g equal secant of x. Okay, so the derivative of x, that's just 1 times g, so that's just secant of x, plus f, so that's x, times the derivative of secant, that's secant x, tangent x, and I'm just going to factor out a secant x to make life a little nicer. And there's your derivative. So there we use some trig properties and the product rule. Hopefully that's pretty familiar with you guys. Okay, the next one we're going to go ahead and do a quotient rule. It's going to be a little messy, but that's okay. So let's say f of x is 1 over the square root of a squared minus x squared, all squared, plus 4. And let's use the quotient rule to solve that. And the quotient rule, the way I remember it is derivative of the top bottom minus top derivative of the bottom all over bottom squared. Okay? Where your top is just your numerator and your bottom is just your denominator. Okay. Well, the derivative of the top will be pretty easy. That's just 1. The derivative of the bottom might be a little messy. So let's try to find the derivative of this guy. And I'm going to rewrite this as such to make it a little easier. This is another chain rule because we have a composition function. So it's going to be a little messy. So we have 1/2, we bring the power down. We keep the inside. We drop this a power. And then we have to multiply by the derivative of the inside. Well, that means we have to take the derivative of this and the derivative of this, but that's a constant, so that's 0. The other one will require another chain rule. So that's 2 a squared minus x squared to the first power times negative 2x, because that's the derivative of the inside. Okay, so let's clean that up just a little bit here. This and this can cancel. So let's see. That is, I could distribute this. I'll just leave it out. I mean, it doesn't totally matter. And then I'm going to rewrite with positive exponents. So this guy, I can move all that down here. And then I'll just rewrite that as the square root. Let's see, did I miss anything? I don't think so. Cool. You could distribute this because they're all to the power of 1. I just chose not to. Oh yeah, and then also this is the derivative of the bottom, right? So what we would have, that's the hard part, but we still have to do the quotient rule. So derivative of the top is 0, that doesn't matter. And the top is just 1. So really, we just want the derivative of the bottom, then all divided by the bottom squared. So this whole mess times the bottom squared. Which the bottom squared will just be, it'll just be this because we square it. So yeah, there we go. We could simplify this further. This is just minus 2x. Oops. A squared minus x squared. And then just multiplying through. It's the same thing as a squared minus x squared squared plus 4 to the first power times a squared minus x squared squared plus 4 to the 1/2 power. And we can just simplify that. What is that, 3/2? So that's just a squared minus x squared squared plus 4 to the 3/2 power. So just adding our exponents. When you're multiplying, you can add the exponents. Cool. So that was messy, but it's the quotient rule. So that's just kind of the way it goes. Let's do some integrals. So we did a bunch of derivatives. Let's do a few integrals. Let's say I want to find the integral from 0 to pi, so it's a definite integral. Sine of theta d theta. So the first thing we want to do, we'll use the second part of the fundamental theorem of calculus, right? Where this is our a, and this is our b, and the f is our antiderivative, and the antiderivative of sine is negative cosine theta, evaluated from 0 to pi. So that's negative cosine pi minus negative, so plus, oops, did that backwards. That should be 0. Minus cosine pi. Remember our unit circle. Cosine of 0, that's what, -1. And then if we go over to pi, let's see, that's, oh no, I did this right. This should be b. Look at me being silly. Okay, so negative cosine of pi is right here. So that's -1, so negative times a negative is positive. Plus 1, just 2. So there you go. That's all there is. Let's try this one. Let's say you have the integral of a constant k over x squared dx. Well, the integral is a lot like a derivative in the sense that it's linear. So we can kind of think of it as you can think of it as the same way. They're both linear. So we can use some of the same properties. And then I rewrote. So I have my x in the numerator. And I guess you could think of the power rule for integrals. The power rule of integrals. So the integral of a to the x and dx is just ax n plus 1 divided by n plus 1. So if you were to add this, that's -1. So you divide by -1. That just makes this negative k x to the -1, or negative k over x. And then we have to add a plus c because this is an indefinite limit, or an indefinite integral. It doesn't have the limits. where the last one did have limits, so it was a definite integral. Let's do this one really quick. What if we wanted the integral 1 of x k over x dx? Well, again, we can factor out the k and 1 over x dx. And here you'll see there's an issue with the power rule, because x to the -1, if you add 1, you're going to be dividing by 0. So this one's a special property. This will just be k, the natural log of x evaluated from 1 to x. And the natural log of 1 is just 0, right? This would be k natural log of x minus k natural log of 1, but that's just 0. So this simplifies pretty nicely to just this. This is, well, let's just do a quick review. So sine of x is odd. It's an odd function, and cosine of x is an even function. And that's important. And the way we test that is you can do f of negative x. Well, let's do an example. I think that'll make more sense. Let's look at sine squared of x. Is that even? Is it odd? What's sine squared of x? And the way we do that is we just do f of negative x is sine squared of negative x, which you can think of as sine of negative x squared, which is negative sine of x squared, which is just sine squared of x. So sine squared of x is actually an even function because we were able to get back to here. Let's try another one. Let's say f of x is 5x to the 5th plus x. F of negative x is 5 times negative x to the 5th plus negative x. Well, a negative to an odd power, that's going to yield us a negative. So this, we would say, is odd. Okay, and if we had, think of it like this, if we had a negative y here and we divided by -1, we would get back to the function we had. So that one's odd. The reason why that's important is because if you have the integral of some limit, the negative limit, the positive limit of f of x dx, and we know that this is an odd function, this is just 0. Think about that. What does the integral tell us? It tells us the area under a curve. And if you remember the symmetry with an odd function, we're going to have the areas just cancel out. Our negative area will cancel with the positive area, assuming these limits are where they need to be. And then you're left with an area of 0. And that's going to save you a lot of time with certain integrals. So that's pretty important. So I kind of ran through that pretty quickly. I didn't go through all the steps. I'm assuming most of you guys don't need that. But nonetheless, we talked about derivatives, the second derivative test, the power rule, the chain rule, product rule. We did a quotient rule, did a couple integrals. Very light warm-up stuff. The reason why I did this is because in the next video, I have a differential equations little thing I want to do. But, I really want to do Taylor series. So that's what's going to be next. I think the Taylor series is next. Maybe I have a differential equation, some complex numbers, maybe some geometry. I have a few videos, just kind of warm-up videos that'll help, and maybe a playlist of these subjects will be more helpful for some of you guys, but just for me in the math methods class I'm taking, brushing up on just kind of, rubbing against these topics a little bit will be really helpful. So hopefully you guys liked it.